Alright, so in the earlier part of this lesson, we talked about the quantity delta x, which is the change in the x values, simply the difference x minus a. And we talked about the quantity delta y, which is the change in the y values, f of x minus f of a. What we haven't talked about yet is the change in L. When x changes from a to x, when the independent variable changes from a to x, what's the change in L? So now we want to consider, what about the change in L? Delta L is, of course, that distance right there. Now we know that the change in y values is the difference here. So we can see from that picture that it's certainly true that the change in y, delta y, would be approximately equal to the change in L. They're very, very close, but they're not exactly the same thing. To be able to talk about the change in the function L, we've got to talk about some new quantities, differentials. dx, the differential of x, is the change in x. Okay, so that's the change, there's an e there, in x values, if I can spell the word value, on the linear approximation function. dy is defined as f prime of a times delta x, and that's how we find the change in L. That is the change in the y's on the linear approximation function. Okay, so in general, for any, this that we have written down is for a particular value of a. In general, for any value of x, dx is simply the difference in the x values. So dx and delta x are the same thing. dy is defined as f prime of x times dx. Okay, and actually, I should have written dx right there. dx and delta x are interchangeable, so if you've got an expression where you're using a dy, you should use the dx in that expression as well. So the differential of y is very, very close to the actual change in y. Now, here's an example. Suppose we have the function f of x equals e raised to the 2x power. If I find the differential of y, that's going to be f prime of x times dx. So in this particular case, the differential of y would be 2 e to the 2x power dx. And if you take that expression, and we could have done this with the general term too, but if you take that last line in that equation and you solve or divide both sides by dx, you'd have dy over dx is equal to 2 e to the 2x power. It's simply a derivative. So dy is the derivative multiplied by dx. Leave that there. Now, how do we interpret this? A small change in x. Okay, that's kind of the key. A small change in x, not a big change in x, because we have to stay fairly close to that particular value, x equal a. And we can think of that small change in x as either dx or delta x, because it's the same idea. Produces an approximate change, and the key is approximate because it's not exact, of 2e to the 2x dx in the function f of x. So, if x changes from 1 to 1 and 1,000th, then dx delta x is equal to 1,000th. Oops. Then the approximate change in y for this much change in x would be equal to, let's see, 2, can't see my equation, e to the 2 times 1 power, so we're plugging 1 into the function, into the derivative function, and then multiplying by that dx. So what that line is, dy is f prime of 1 times dx. So the decimal approximation for that expression is 0.01477. So we could say that the approximate change in f of x that corresponds to this amount of change in our x values is 0.01477.